So our final video for Chapter 9 and for all new material in the course will be this last example, modeling COVID-19 infection in the U.S. So we have some data taken from cdc.gov. This was collected on April 19th, 2020, and the data starts on January 22nd, 2020. This is week 0 in the table, and that's when our first case of COVID-19 was reported in the U.S. So what we're interested in doing is modeling this. I think most of us, as soon as we think about modeling an infectious disease, will react by saying this must be an exponential model. So that's true, but let's see why that's the case, and let's compare some exponential models to some linear models and be mathematically certain about that decision. So it being our aim to model this infection rate, we should consider some first things from this data. Now, what we actually have, what actually came from cdc.gov in regards to this data is this table right here. And note that this is weekly data. The data that's reported on the website is actually daily, but if we did daily, we'd have 12 times 7, 84 days on this table that we'd have to look at. So to simplify our analysis, I just collected it as weekly reports. So let's complete some things. So the first thing we want to think about is the absolute change in infections. Right, from week to week, what our absolute change is. Remember that this is just, well, if it's the average absolute change over the course of the week, it's number of cases in week 1 minus the number of cases in week 0, that's this value, divided by however long has gone by, that's week 1 minus week 0, so 1 week has gone by, so that's 4 cases per week, 6 cases per week in this case. So we're asked to complete this table wherever it's blank. So we come down here and we realize we have 15 cases in week 7 minus the 98 that there were in week 6. And we divide that by week 7 minus week 6, which is just 1, and 1 is actually the denominator in all of these, so it's kind of extra information that we don't need, but to be more general about this problem, it's good to do that. 1,117 is our absolute change between week 7 and week 6. If we do the same in the very bottom here, the absolute change from week 11 to week 12, the difference of these two numbers, larger minus the smaller, and we end up with our more recent minus the older, 205,088. So these are our absolute changes. Now, we use absolute change to consider whether or not something has linear growth. So in other words, if our absolute change is constant, all the numbers in this column are somewhat equal to each other or exactly equal to each other for perfect linear growth, then we've got a linear growth situation. Well, it's pretty obvious that a number like 2 and 9,227 aren't very close in value, so it's extremely unlikely that this is linear growth. But we'll still consider linear models just to look at them on the graph anyway. So we move over to relative increase or relative change. Remember that this tells us, if we have a constant relative change, this tells us that we're dealing with an exponential model, or suggests that we might be dealing with an exponential model. So in order to come up with our relative increase per week, we'll do cases in the more recent week minus cases of the previous week divided by cases of the previous week. In other words, that's new minus old divided by old. Same old relative change formula we've always dealt with. So, places where this hasn't been filled in, down here in week 8, what was our relative change from by the end of week 8? Well, we need to look at 10,442 minus 1215. We'll divide that by 1215, the old value, and what we get out of this is 7.56. Now, these are all just decimal numbers. They haven't even been converted into percentages. So this is actually, up top, 400%, moving the decimal 2 to the right, 120% in this case, again moving the decimal 2 to the right. This should be done all the way down here if we wanted to see these as percentages. 756% increase. It's not necessary to do so, but just to put things in perspective, these are large increases per week. For our last column down at the bottom, do the same calculation, 632,548 in parentheses, and that's minus 427,460 divided by, we're going to run out of room, 427,460, the old value, and this is approximately equal to 0.480. So that's 48% down at the very bottom. So again, if we comb through this column, we see that, well, though our instinct was to say that this is an exponential model, we have some very different numbers for the relative change. 0.09 is pretty far off from 11.4. They're not very close in value. So it even questions whether or not this is an exponential model. But once we have a look at the data and the points plotted on a graph, we might be able to make a better decision about it. So let's have a look at that. Moving into the linear model, we're asked to form two different linear models. And now this is completely arbitrary. So we can form a linear model that connects week 0 to week 8, or week 0 to week 6, or week 4 to week 10. We can choose anything. So this question just sort of gives us some arbitrary places to start. We're asked to do one between week 0 and 8, and another one between weeks 8 and 12. All right, if we look at that in pictures, before we even come up with that value, or what that line's equation is, week 0 to week 8, that is this point to this point. If we connect the line through those 2 points, I think it's pretty obvious what our model is going to do. If we have a line that connects these two, this model underestimates, and it's actually not very well drawn. Let me try again. It underestimates our infection rate. These are actual numbers of cases, and this line is well below it. So we've missed in that sense. When we form the other line, week 8 to week 12, let's see what happens there. Week 8 to week 12, we're going to connect here to here. And this might be okay for predicting short lengths into the future, but notice that this curve might get steeper and start to miss this line as we continue indefinitely. Also, the back end of this is pretty troublesome. It doesn't really cover what happened early on in the infections. So we already see the flaw in either of these linear models. Now to come up with the equation for these lines, just in case they were worth considering. Let's do it. So remember how to find the equation of the line between point 0, 1. This is week 0, and the number of cases in week 0 was 1. And then this was for week 8. The number of cases in week 8 was 10,442, drawing this from the table on the previous page. Now, the slope in this case, M1, is the y value, 10,442, minus the y value of 1 in each point, or the cases, case minus case over week minus week. 8, week 8 minus week 0. This week corresponds to this number of cases, so they're above each other in this slope equation. What this comes out to is, well, approximately 1,305.1. We'll just round it to one decimal place. It's arbitrary. We're just not asked to keep any decimal places, so we'll pick it on our own. Now this is our slope. Y is equal to 1305.1 x, just like t in our exponential models, x will just be a variable, plus b1. The last thing we need to figure out is b1. b1 is our y-intercept. Our y-intercept occurs when x is equal to 0, when we're down here at this end of the graph. Now we're not really, in our case, it's kind of easy to see. When x is equal to 0, we have that y is 1. So we can plug this into an equation that looks like 1 equals 1305.1 times 0 plus b1. And this is the same as 1 equals 0 plus b1. So b1 is just 1. solving for b. You can use either of the 2 points to solve for b1 to come up with this value. We could have used this point as well to come up with the same thing, solving for b with known values of x and y. Now, in full, our equation is the following. We've got y equals 1305.1 x plus 1. So there's our linear model. Remember, this line was too flat. It passed through here and here. It just isn't going to model the later stages of this infection across the population. So we didn't like that one. We also didn't like the other one, whose equation actually turns out to be doing the same thing. I'll put the 2 points down, but let the student practice the rest of the details. Our 2 points are 8 and then 10,442. And then the latter value is week 12 with a case number of 632,000. Again, all from the table on the previous page, 548. So this is going to come out to y equals, and there's some work, you just basically follow the steps from above. 155,526, just rounding to 1 decimal place, times x, minus 1,233,770. Okay, so the real problem with this model is, imagine what happens if you want to check what week 0 presented. In other words, project into the past, which is something we should already know, but just to see how good a model is doing, you might want to check how it looks in the past. Well, if you plug in week x equals 0 for week 0, the value you get out from this formula is negative 1.2 million. We didn't have negative 1.2 million cases in week 0. In fact, there's not really any meaning for that. So this is what a lot of mathematical models will have, are some artifacts in it that just don't meet with reality. It's just leftover theoretical bits that don't match up with actuality sometimes. One of the troubles of modeling things. So, lastly, we're asked to address the shortcomings of each of these. Well, the first model, week 0 to 8, that was too flat. Too flat. And week 8 to 12, well, that was here to here, if we were to draw that line. That's not bad, but it's only good for, I don't know, maybe week 8. Maybe we can go back to week 6. Probably not, though. Week 8 to max week 14, right? Because remember, this whole curve, these points might be getting steeper and steeper, and not really following the value on a line, right? And we'll be underneath that point I just added there by just a little bit in week 13 or 14, and we're going to continue to miss. So those are the challenges that we'll face in these models. Linear is certainly not the way to go. We knew that from the table, and we can see it from this picture as well. For the exponential model, our last situation, we're gonna make 2 exponential models, and for the same time periods, weeks 0 to 8, and then weeks 8 and 12 again, and we'll compare these. Now, we need a growth rate. So in order to come up with that, we have to be a little bit clever about it. Remember, our growth rates per week could be anything in this entire column right here. Since they're so varied, it's kind of difficult to pick which one we should go with. So there are arbitrary ways of going about that. And again, this is something we need to note. The experts who are in control of putting these models together have to face these dilemmas. A table of numbers like this, which is the most appropriate to choose to build your model? So let's see the two different ways it could possibly go. So from week 0 to week 8, remember again that our 2 points were 0 to 1 and 8 to 10,442. Okay, the problem suggests just one possible way to come up with one of these rates. So let's say that our rate R from week 0 to week 8 is the number of cases in week 8 minus number of cases in week 0 divided by the number of cases in week 0, so new minus old over old, and then we'll divide by the number of weeks to get the average rate of change per week. This is just one way to do this. It's not an official way to do it, it's just what's suggested for this problem. So Q1, the model we're looking for, oops, we're not ready for Q1 yet. We need R to begin with. We need R, and R is going to be 10,442 minus week 0 had one case divided by 1, and this is all divided by the number of weeks that have gone by. 8 minus 0 is 8 weeks. 8 minus 0, or 8 weeks. The value that we get after plugging this into a calculator is approximately 1,305.1. It looks familiar because we're using this division by 1 right here. That's the way that R has come out to be so familiar to us. So that's a really large rate. That's move the decimal place 2 more to the right, and you've got the percentage. That's in the tens of thousands as a percentage. So, hundreds of thousands as a percentage. Our model now is this. Q1 of t is going to be equal to our initial population. Well, since we start in week 0, our initial infection population is 1. 1 times, and then 1 plus R is 1 plus 1305.1 to the t. And just to clean up the model a little bit, we don't need this product of 1 since it's just going to be the same as the number we've got in parentheses. And we'll add 1 to 13,005.1, and we'll have 13,006.1 all raised to the t power. Now again, just like that linear model, we want that t to be there. This is our model. This is our predictor for how many infected we'll have, q, after a time t into the future. So our next model is very similar. I'll write the points down, and following the same steps, we'll get the same value. We'll have for weeks 8 to 12, we end up with a model that looks something like q of t is equal to 10,442 times 15.9 to the t. That R might have been approximated along the way, but we follow the same steps. The numbers for week 8 and week 12 that we had previously. We'll find R in the same manner as above. 1 plus that R ends up being this. You need to check. And then this was the number of cases we had in week 8. Q naught in this case. Okay, so let's compare some calculations from each of these models. What's Q of 12 for model 1? So model 1, Q of 12, that's 1306.1 to the 12th power, and this ends up being somewhat astronomical. This is something like 2.46 times 10 to the 37th. So 10 to the 9th is a billion. There are only about 7 or 8 billion people on the planet, or maybe at most 9 billion. I'm forgetting offhand at the moment. This number is way too large. There are only tops, just because I can't remember right away, 9 billion people on the planet, which is 9 times 10 to the 9th. So that's the key thing. This 10 to the 9th, 10 to the 37th. This means the entire population's infected by, and the entire world's infected by week 12 with this model. Well, we know that wasn't actually the case. Week 12, we had 600-something thousand infections. So this is Q1 overestimates badly. Goes off the chart. Overestimates. Okay, let's try Q2 of 0 for our second model. So what happens at 0 for that? Well, Q2 of 0, well, it's going to be a little bit different than what we expect. 10,442 using the values we have above, 15.9 to the 0th power. Well, that's a 1. This number raised to the 0th power is 1, so this is just 10,442 times 1, which is just itself. Well, in week 0, we had 1 case. Well, this model actually doesn't touch on week 0. Is that week 0? This is not week 0. This is amount of time. This is 0 weeks after week 8. Okay, so Q2, what Q2 doesn't do, it doesn't account for the beginning of infection. So that's maybe its drawback. However, it might be relatively accurate for the most recent. And in fact, of all the models we've looked at, I think that Q2, if we were to look at it again into the following week, into the 13th week as that data becomes available, I think that we'll find it's the most accurate prediction of all the estimates. So hopefully what we've seen is that this modeling situation is not easy. It's hard to come up with these choices. There are more highly sophisticated ways to come up with these values of R and adjust what's called our parameters, the constants in these models, but that's beyond the scope of the course. But this is just to give us an idea of what kind of challenges we're facing in this overall. So complete the parts that I didn't, and good luck with these problems.